Suppose we want to consider this dynamical system. It's a simple concentrated mass pendulum. The parameters are the following. Theta, theta dot, and theta dot dot are respectively the angular position, the angular velocity, and the angular acceleration. L, that indicates length, m, which is the mass, h is the damping coefficient, and g is the gravity constant, which is an acceleration. Remembering that the moment of inertia for a concentrated mass is I equals ml squared, and that Newton's second law in rotational form is the sum of t, where t is the torques, equals I theta dot dot. And since we have the gravitational torque as minus mgl sine of theta, and the dampening torque which is minus h theta dot, from the torque balance we know that this system can be described by the following ODE. ml squared theta dot dot equals minus mgl sine of theta minus h theta dot. Isolating now theta dot dot, we get theta dot dot equals minus g over l sine of theta minus h over ml squared theta dot. Now, how do we evaluate the stability of this dynamical system? For this simple example, an analytic solution can be found, but in general it's either extremely difficult or straight up impossible to obtain one. Now we're left with two possible options: a numerical solution, so we solve equations with a computer, or a simplified approach to obtain key information about an approximation of this problem. In this video we will explore the second option, but to do that we first need eigenstuff. If you ever encountered eigenvalues or eigenvectors in your math path so far, at some point you probably thought, but what do they actually mean? Like, why do we care so much about them? Many people I personally know simply mechanically learn how to calculate them with the blessed formula determinant of a minus lambda I equals 0, without any real understanding or intuition behind it. Whether you've struggled with these concepts in class, you want to build real intuition, or simply a refresher on this topic, then this video is for you. Also, if you're just curious about the neat application of this eigenstuff to the example problem, stay until the end, or skip here. If you've not found an answer to the questions I asked before, then this might be the time. If you've ever taken a linear algebra course, I'm sure you know what they actually are. Or do you? To have a clear understanding of this video, you just need the absolute basic concepts of analysis, like sets, functions, domain, and codomain. Matrices. Matrices are beautiful. They may seem scary, unnecessarily complicated, or intimidating at first, but they are actually powerful tools, and they help us understand and manipulate entire spaces. Repeat after me: matrices are your friends. But as long as we think of them just as tables of numbers, we cannot understand their real power. We must think of them as transformations, linear transformations to be exact. First of all, we work in vector spaces. But what are they? Well, a vector space is simply a collection of objects, called vectors, where you can add them together and multiply them by numbers, or scalars, and all the usual rules that you know about addition and multiplication still hold. Think of arrows in a plane, but they can be much more abstract objects that just follow similar rules. Imagine that you have a piece of fabric and you draw a picture on it. You can think of it as a 2D space. If you stretch it, flip it, or rotate it, you're applying a transformation, just like a matrix does to vectors. So we can think of a matrix as acting on an entire vector space, transforming every vector in it according to certain rules. Let's see it visually. Now we draw some arrows on our picture, and we do the transformation. Notice that some directions on our fabric are special. When you transform it, the arrows pointing in those directions only get longer or shorter, but they don't change direction. Those special arrows, they're the eigenvectors. How much they stretch or shrink, that's the eigenvalues. To have a better understanding of this step, I highly recommend Free Blue and Brown's video on this topic. Keep in mind that eigenvectors are not unique, and they simply identify the direction, or to be more precise, the space, which is called the eigenspace, generated by the eigenvectors corresponding to a specific eigenvalue. This depends on the algebraic and geometric multiplicity of the eigenvalues, which is something a little bit more advanced that we'll see later. For example, considering a simple eigenvalue, which means its multiplicity is equal to 1, if we find one eigenvector to be v equals 1, 1, then any multiple of that vector is still an eigenvector. So we can say it defines the eigenspace span of v. So if we use a floating variable t that can assume any real value, any vector tt is an eigenvector. We said 1, 1 is an eigenvector, but also 2, 2, 3, 3, negative 1/2, negative 1/2, still an eigenvector. The formal definitions are: v in our vector space excluding 0 is an eigenvector of f if there is a lambda in K such that f of v equals lambda v, where K is an arbitrary field. Notice that we exclude the null vector since it will always satisfy this rule. The scalar lambda is the eigenvalue associated with the eigenvector v. The set of vectors v of lambda, v in v such that f of v equals lambda v, is called the eigenspace of f associated with lambda. In other words, v of lambda is the set of eigenvectors of f associated with lambda plus this zero vector. But how do we actually find these special directions and their stretch factors? Well, mathematically, an eigenvector v of a matrix A satisfies A times v equals lambda times v, where lambda is the eigenvalue. To find them, we need to solve the equation A minus lambda I times v equals 0, where I is the identity matrix. This leads to the so-called characteristic equation, which is determinant of A minus lambda I equals 0. We just need to solve this equation for lambda and we find the eigenvalues. This is the famous equation that everybody remembers, and some use it mechanically without any real intuition behind it. Once we have the eigenvalues, plugging those lambda values back in and solving for the corresponding vectors v, we find our eigenvectors. But why does this formula pop up? Well, think of it this way. We are looking for vectors that after the transformation by A are just scaled versions of themselves. This equation A minus lambda I times v equals 0 means that for simple algebra. When you subtract lambda times the original vector from its transformed version, the result is still the zero vector. Remember that since v equals 0 makes that equation true for every possible value of lambda, the zero vector is not considered an eigenvector, even though it satisfies the equation. The definition of eigenvectors exclude the zero vector by design because it contains no directional information. Thus, we search for a kernel of A minus lambda I that accepts solutions other than the trivial v equals 0. The matrix A minus lambda I must then be singular, as we are searching for an eigenspace that, if it exists, must have at least dimension 1. The rank of the matrix then has to be lower than its size, and it's not invertible. Thus, the determinant being 0 ensures that there are non-trivial solutions for v. Now, the characteristic equations also generates the characteristic polynomial, an extremely important property of matrices. This polynomial contains some crucial information about the matrix, like its trace and its determinant. Let's see an example of our 2x2 matrix. It is possible to prove that this is true for any matrix size. For the generic nth grade matrix, we have P of A of lambda is a polynomial of grade n, P0 is always the determinant of A, Pn minus 1 is always the trace times a negative 1 elevated to n minus 1, and Pn is always minus 1 elevated to n. Let's now calculate eigenvalues and eigenvectors for a simple example. Once we have built an intuitive understanding of eigenvalues and eigenvectors on a two-dimensional plane, we can take the concept and elevate it to an arbitrary number of dimensions. What's an important take-home point? Well, since we are working with vectors, every input of the transformation, which is a vector, can be expressed as the sum of the contributions of vectors of a basis. If we can write a basis of eigenvectors, and we will see later how to do that, we can write any vector as a linear combination of eigenvectors. Thus, every vector will be stretched at most as an eigenvector, which means at most by a factor equal to the biggest eigenvalue. We call the eigenvalue with the biggest absolute value the spectral radius. The spectral radius tells us a lot about the system we're analyzing, like the kind of values a matrix tends to when it is elevated to higher and higher powers. This will seem a bit random, but please try to trust me on this definition a little bit. It will be very useful later. A neat property of matrices is that some can be diagonalized. What it means is that for a given matrix A, it is possible to find a similar matrix D which is diagonal. For example, two matrices that represent the same transformation with respect to a different basis are similar, and the matrix S is a change of base matrix. If we can do a change of basis and have our transformation with respect to a basis of eigenvectors, then that matrix will be diagonal. Let's see this for a simple example. So we found that matrix A is similar to matrix B, which is a diagonal matrix. So A and B represent the same linear transformation, but A is in the standard basis B, and B is in the new basis B prime. Since B is diagonal, the transformation is now easier to analyze, and we know that the basis B prime consists of eigenvectors of A, and it has on the diagonal its eigenvalues. Why? Well, that's because every eigenvector is only stretched by its corresponding eigenvalue, so multiplying the matrix by the eigenvector must return only scalar times that eigenvector, which is its eigenvalue. Considering the rules of matrix vector multiplication, we only get a non-zero result for that eigenvector. Then we have to transform it back into the standard basis if that's what we want. An important property of similar matrices is that they share what we call similitude invariants, which are the rank, trace, and determinant, and the characteristic polynomial, so its coefficients and roots too. We can quickly prove this property. So if matrix A is similar to matrix B, we have the following. So, a matrix is diagonalizable if there exists a basis of eigenvectors, and the matrix is similar to a diagonal matrix that has the eigenvalues on its diagonal. We seek diagonalizable matrices, so we want to build a basis of eigenvectors. For a set of vectors to be a basis, they need to be linearly independent, and their linear combination must cover the entire vector space. Imagine now calculating the eigenvalues. We find the same eigenvalue multiple times. We say that that eigenvalue has an algebraic multiplicity greater than 1. For example, if the characteristic equation is lambda minus 1 squared equals 0, we know that the eigenvalue lambda equals 1 has algebraic multiplicity 2. We now calculate the eigenvectors associated to that eigenvalue. If we find that the associated system has more than one degree of freedom, then the geometric multiplicity is greater than 1, like in this example. An eigenvalue is regular if the two multiplicities are equal. If an eigenspace has dimension more than 1, it just means that there is a space with more than one dimension whose vectors are eigenvectors of the same eigenvalue. If an eigenvalue's multiplicity is 2 and it is regular, it means that there is a plane whose vectors are all scaled by the same amount without being rotated. Note that the geometric multiplicity is always less or equal to the algebraic multiplicity. If an eigenvalue is regular, then the eigenvectors are enough to build a basis of the vector space. If the geometric multiplicity is smaller than the algebraic multiplicity, the eigenvector is called defective and there are missing eigenvectors. It means that there are not enough to cover the entire space with the linear combination, so we cannot have an eigenvector basis. This means the matrix is not diagonalizable. Now there are some more advanced tools to do this, like generalized eigenvectors or the Jordan canonical form, which is the next step if a matrix is not diagonalizable, but that's a story for another day. Why would we diagonalize? When a matrix is diagonalizable, everything becomes much easier to compute, like raising the matrix to a power, solving differential equations, or simulating systems. I need to confess something. I haven't been completely honest with you. It is not strictly true that real matrices can only have real eigenvalues, and thus that the eigenvectors can only get stretched. There can also be complex eigenvalues that are characteristic of rotation scaling matrices. For real matrices, these always come in conjugate pairs, which means that they have the same real part and opposite imaginary parts. Let's see an example with a 2D rotational matrix. This matrix rotates the vectors by the angle theta counterclockwise. For simplicity's sake, let's see the example where theta equals pi half, which means 90 degrees. So if a real matrix has complex eigenvalues, it means its transformation cannot be described by just stretching or shrinking along real lines. Instead, it corresponds to a rotation or a spiral in the vector space. The magnitude, which is the square root of the sum of the squares of the imaginary and real parts, tells us how much the vector is shrink or stretched. The argument, which is the angle, tells us how much the vector is rotated. As we will see later, using Euler's formula, we will be able to connect these properties to the amplitude, frequency, and growth or decay of physical systems. Even when eigenvalues and eigenvectors are complex, we can always build real solutions by combining conjugate pairs, and this leads to sines and cosines in physical systems. So, why does this matter? Eigenvalues and eigenvectors show up literally everywhere. In physics, they describe how things vibrate. In engineering, they help us check if a bridge or a building will wobble or stay stable. In web search and data science, they help rank pages and compress images. In electronics, they tell us how reactive circuits behave. Whenever you want to understand how a system changes or what its natural modes are, eigenvalues and eigenvectors are your secret weapon. I cannot possibly make extensive examples for each of these in this short video, so I'll do my best to explain a single concept from control theory in an in-depth way. Let's now use all the knowledge we amassed so far to finish our pendulum problem in the beginning. To do that without a numerical solution, we need to do the model analysis of an LTI system. Suppose we have any physical system, like a mass spring damper or even a building during an earthquake. Near its equilibrium points, we can linearize the system, and assuming that its behavior does not change with time, as in, given the same initial conditions and inputs, it will always react in the same way, we can model it as an LTI system. Then, the differential equations that describe its motion can be written in terms of matrices. The most important matrix is called the state matrix. When we solve these equations, the eigenvalues tell us about the system's natural frequencies and also how fast vibrations die out, their decay rate. To represent a dynamical system in continuous time with a system of ODEs, remembering that for any ODE of nth grade, we can write n first grade ODEs, where x is the vector of the state variables, y are the outputs, and u are the inputs. If the vector equations f and g are linear, then we can write the system as the following. This is called the state space representation, and A is called the state matrix. If we now assign some initial conditions x of 0 and give an input u of t, Through Lagrange's formula, we obtain x of t, which is the state of the system in time. Let us consider the first row, dropping the vector formalism in the written representation. To solve this ODE, we first consider the homogeneous solution, so the solutions when u of t equals to 0, with initial conditions x of 0. The system is linear, and the general solution is the sum of the homogeneous solution and a particular solution due to the input. We now use Lagrange's method of constant variation, from which the formula takes the name, and we find the particular solution. V is an unknown vector function to be determined. We finally found our solution, which is Lagrange's formula. The first term is called free movement, since it depends only on the initial conditions, while the second one is called the forced movement, since it is determined by the input u of t. The exponential matrix is defined as follows. Free Blue and Brown has another banger video on this, so check it out if you seek any further information. What we care about for now is that for diagonalizable matrices, getting the exponential matrix is pretty straightforward. For non-diagonalizable matrices, we either have to use the definition or Jordan's form. Near an equilibrium point, we can linearize a system. By definition, an equilibrium is reached when u of t equals u constant, x of t equals x constant, and y of t equals y constant, so when the output and the state are steady when the input is steady. Naturally, when this is true, then necessarily also x constant dot is equal to 0, since it is constant. Let us now show the displacements. To linearize, we rewrite the system showing the displacements and use Taylor series at the first order, which is a linear approximation. Since we are considering vectors, the partial derivatives are actually matrices. Right now we only care about the state matrix of the linear system, which is actually just the Jacobian matrix. By using the same logic, we can also obtain the matrices B, C, and D for the linearized system. If the system is time invariant, then these four matrices are made up of constant numbers, since we are analyzing in an equilibrium point, which means when the input is constant, for a system whose equations don't change with time. We want to think about the stability of the system, wondering what would happen near an equilibrium point if the initial conditions aren't perfect, and in the real world they will never be. So let us consider now two different types of movement: nominal movement and perturbed movement. These are generated by the same system with the same input u of t, but with different initial conditions. To discuss the stability, we want to know the value of the norm of their difference. A system is Lyapunov stable if for each positive value epsilon there exists a positive value delta, so that if for each initial condition, so that the difference between the perturbed movement and the nominal movement is less than delta, then the norm of the difference between their movement in time is less than epsilon for each instant of time. If the movement is stable and the limit for t towards positive infinity of the norm of the difference between the perturbed and the nominal movement is equal to 0, then the movement is called asymptotically stable. By applying Lagrange's formula, we find both the nominal and the perturbed movement starting from different initial conditions. Calculating their difference, we see immediately that since we assume the input to be the same, the forced movement must be the same. Thus, only free movement is involved with the stability calculations. We just found an analytic and explicit formula for stability analysis. We should also note that the difference does not directly depend on the nominal movement, which is the specific movement at hand. This means that for an LTI system, every movement is stable, unstable, or asymptotically stable. We can say that for this class of systems, stability is a system property. Also, delta x of 0 takes the role of just a rescaling factor and does not alter the temporal evolution of delta x of t, and it doesn't alter system properties. Looking at delta x of t's evolution over time, we can say, if it stays limited and we have a stable movement, if it does not stay limited and we have an unstable movement, and if it stays limited and the limit of t towards positive infinity of delta x of t equals 0, then we have an asymptotically stable movement. As we said earlier, for a diagonalizable matrix A, its exponential matrix A to the power of at is obtained as follows. So, by analyzing the evolution of the terms e to the lambda it over time, we can analyze the stability of the system. We call those elements the modes of the system. For a diagonalizable matrix, the modes depend on the eigenvalues, and they can either be real or complex conjugates. The second one comes from Euler's formula. For more information on what this crucial piece of maths means, please take a look at this video. For non-diagonalizable matrices, we need to use some more advanced math, which is Jordan form, and just trust me if I say that for non-regular eigenvalues, we get these values for real or complex conjugate eigenvalues. Why does a polynomial part appear? Well, intuitively it happens because A does not have enough eigenvectors to absorb the entire exponential dynamics. The system's response then compensates with generalized eigenvectors, which, under the action of the matrix A, introduce successive derivatives of the exponential, polynomials. Now we analyze each case. So we have real and regular eigenvalues, and as we see there is a very different behavior if the real part is either negative, positive, or null. And we have complex conjugate eigenvalues, regular, and in this case we see the same trend but with an oscillatory part. In the graphs there are the envelopes of the just exponential parts in dotted lines. For real and effective eigenvalues, we see a similar trend, but we need to keep in mind that we are multiplying our exponential by a polynomial. So for positive real parts, it should to infinity anyway. For negative real parts, it starts at 0, since t to any power in 0 is still 0, then quickly rises, but then goes down again, since the exponential for t which tends to the infinity is always smaller than any power of t. And for null real part, we do not get a constant, but rather a constant times a polynomial, so it grows. In this case, it's not stable. And same thing with complex conjugate defective eigenvalues. This time again, the envelopes for the oscillatory part are shown. We can now calculate delta x of t's evolution with time, knowing that each component of the vector, which means the difference for each state variable, is determined by the corresponding mode. We can now define a formal criterion for assessing the system stability, called the eigenvalues criterion. An LTI system is asymptotically stable if and only if all eigenvalues of its state matrix A have negative real part. It's simply stable if and only if all of A's eigenvalues have negative real part and there is at least one eigenvalue which has real part null but is regular, and unstable if and only if there is at least one of A's eigenvalues for which one of the following is true. It either has positive real part or it has zero real part but is defective. Visually, we can show it in a graph like this. Actually, there is a bit of a caveat if the system was non-linear and we linearize it. In this case, we need to use the modified eigenvalue criterion. A non-linear system is asymptotically stable if all eigenvalues of its linearized counterpart states matrix A have negative real part, and unstable if at least one of A's eigenvalues has positive real part. Note that the conditions have become only sufficient, not necessarily insufficient like before. Also, if there are eigenvalues with zero part, we cannot say anything about the system stability. That's because we did a first degree approximation, and intuitively we can see in the example that a stable and unstable systems, when linearized, can be the same. Finally, we can solve our problem. We left our pendulum after finding its ODE. Now let's write the system in state space. where x1 equals theta, x2 is theta dot, and y, so the output is x1, because we're interested in the position of the pendulum. Let's now find its equilibrium states solving a nonlinear system. We found these two solutions. x11 is 0 and x12 is pi. Intuitively, we already know that one of these equilibrium points will be stable and the other one will be unstable. A pendulum is stable in the low position while it is unstable in the high position. But to do a rigorous analysis, we need to linearize the system. We linearize now around the first equilibrium. Now, we need to calculate the eigenvalues, but we can be smart about it. Since we just want to know whether the real part is negative or not, we can speed the process up quite a bit. For a 2x2 matrix, its characteristic polynomial is, as we said earlier, the following. Since we proved that the trace and the determinant are invariant, it means that they are the sum and the product of the eigenvalues respectively. So we have that for real eigenvalues, if the sum is negative and the product is positive, the only possibility is they both are negative. For complex eigenvalues, where lambda 1, 2 is alpha plus or minus I beta, we know the determinant is always greater than 0 unless lambda is real, and the trace is negative if alpha is less than 0. Then we get that for a second-grade characteristic polynomial, a necessary and sufficient condition of stability is that all of its coefficients must be concordant in sign. In our case, let's do the calculations. And now let's check the signs. The signs are concordant, thus the system is asymptotically stable near the first equilibrium point. Let's now do the same calculation for the second equilibrium point. Checking now the signs, we see that they are discordant, thus the system is unstable near the second equilibrium point. This concludes our research and also checks out with our intuitive real-world understanding of a pendulum. But what about discrete time systems? A system is in discrete time if its state variables, and the system itself if it is time variant, evolve in time according to k in n, so time can only assume integer values. If we know that the world is in continuous time and not discrete, why do we care so much about this type of systems? Well, there are various reasons, like the fact that they behave nicely with asynchronous events and iterative numerical algorithms, in which k becomes the number of iterations, but the most important one is that it's the way that computers see the world. An extremely common occurrence is in fact of having continuous time systems, which means in the real world, controlled by a discrete time controller, a digital one. Since in discrete time we cannot do derivatives, we use difference equations. And for an LTI system, this becomes the following. It is possible to extend the concept of Lagrange's formula in discrete time too. If we do our model analysis, we discover that, in the same way it did in continuous time, the stability depends only on the free movement, and thus on a to the power of k. Once again, if a is diagonalizable, we can easily find the modes. We see that for positive values of a, the behavior changes drastically depending on the fact that it's greater, equal, or less than 1. And we see a similar behavior pattern for negative values of a. What's the catch? Is that in discrete time, we can have oscillations also with real eigenvalues if they're negative. This suggests the eigenvalues criterion in discrete time, which then extends to complex eigenvalues. An LTI system in discrete time is asymptotically stable if and only if all eigenvalues of its state matrix A have magnitude less than 1, simply stable if and only if all of A's eigenvalues have magnitude less than 1 and there is at least one eigenvalue with magnitude 1 and it is regular, unstable if and only if there is at least one of A's eigenvalues for which one of the following is true, either the magnitude is greater than 1 or it's equal to 1 and it is defective. This directly connects to the claims we made about rotation and resize about complex eigenvalues before. For a discrete time system, if we can find the spectral radius, we already know the stability properties just from one eigenvalue. Moreover, in general, the spectral radius is often easier, or at least cheaper, to approximate than computing the full set of eigenvalues, especially in large numerical algorithms. We have iterative methods that can approximate it efficiently, like the classic power method, which converges to the eigenvalue of largest magnitude and only requires matrix vector multiplications, which is generally cheap. And we don't need to factor or decompose the matrix like in QR or Schur decompositions used for getting the full spectrum. Full eigenvalue decompositions, like the QR algorithm, have complexity O of n to the power of 3 for dense n times n matrices, and for large matrices it becomes prohibitively expensive unless you absolutely need all eigenvalues. Hey, I really hope you enjoyed this video, whether it was because you needed the refresher or because you liked the model analysis. Ideally, this video helped those who struggle with math as well as those who are curious about the topic. I tried to think of a way that could leave everyone happy. I'm a student in aerospace engineering, and I thought I could give you a sneak peek at the ways eigenvalues and eigenvectors are used in practice. I've always been a practical learner, meaning that I could never truly understand something unless I got an intuitive understanding of it through real-world applications. The Calculus 1, 2 and the linear algebra courses were especially challenging for me to grasp initially, since I lacked practical applications of these concepts. But once even more difficult courses came along, such as numerical calculus or automatic control systems, I finally saw their implementations and I had a much easier time. I could finally see abstract things into action, and this definitely helped me. I might start making more videos, particularly a series on numerical analysis and how to use computers to solve physical and mathematical problems, but I'm not really sure, because the semester is starting soon and it's gonna be tough. This is everything for today. Feel free to leave a comment for any question or suggestion, and until next time, cheers! For real matrices, these always come in conjugate pairs. Pairs? Pairs?